Welcome to session AIM 406, Implementing MLOps Practices with Amazon SageMaker. How many of you are in the position where you have a few proof of concepts or projects that you built using Amazon SageMaker, and because of the business value gained off of those first few projects, you now have more projects in the pipeline, and you need to find a way to scale the deployment and management of those machine learning workloads? I'm Shelby Eigenbrod, and I'm an AI/ML Specialist Solutions Architect at AWS. And I specifically spend a lot of time with customers on operationalizing machine learning workloads and adopting MLOps practices. Today, I'm going to walk you through applying MLOps practices to Amazon SageMaker workloads so that you can better support, manage, and scale the number of machine learning workloads that your business can benefit from. Today, we only have 30 minutes, so we'll do a quick introduction followed by a deeper dive on how you can automate SageMaker workflows, and then begin applying CI/CD practices to those workloads. So let's get started. Much of the content for this session is really targeted for anyone that is tasked with creating machine learning workflows or pipelines, and that persona that performs those tasks can vary quite a bit across customers, organizations, or teams. So whether that happens to be a data scientist, an ML engineer, or a DevOps engineer, regardless of the role or title, if you're tasked with creating machine learning workflows or pipelines, then this session is for you. Now, this is a 400 level session, so we make some assumptions on prerequisite knowledge coming in. But for those that aren't aware, Amazon SageMaker is our end-to-end machine learning platform, offering core capabilities and features across data preparation and data labeling, model building, model training and tuning, as well as the deployment and ongoing management of your models. Amazon SageMaker is built so that you can choose to take advantage of all features by using it end-to-end, or you can choose to use only the features that you need for your specific use case. The level of modularity allows you to easily tap into the features and benefits of SageMaker within your machine learning pipelines. Now, the topic of MLOps is much larger than a 30-minute session, and while we understand that MLOps, just like DevOps, is really about the intersection of people, process, and technology, we're really only going to focus on technology, and even more specifically on automated workflows and CI/CD pipelines in this session. Just as we use automation to support the underlying practices of DevOps, we do the same for MLOps. A common step is to start by applying automation to avoid manual tasks and create repeatability. Then starting to take those automated workflows and apply CI/CD practices such as source and version control, automated quality gates, and deployment orchestration to higher level environments where you may want to integrate with other systems and applications. Now, these diagrams are just simple diagrams that represent high-level references with common steps and components, and the reason they're so high level is because there is no such thing as a single golden machine learning pipeline that meets every use case, including the variety of algorithms, frameworks, existing tooling, deployment patterns, and even the organizational structure in terms of what roles are responsible for the various tasks in your pipeline. There's a lot of valid ways to apply MLOps practices from a technical implementation standpoint. So the key is not so much in the detailed implementation choices, but more around the goals and the strategy of what your pipeline should include, what skill sets you may have in-house today, and understanding all of the potential pipeline dependencies. Once those are outlined, the technology is the easy part. And today we're going to focus on using the features of SageMaker combined with other AWS services to illustrate automated workflows and CI/CD pipelines. First, let's start by applying some simple automation to a typical machine learning workflow. So as we've worked with customers to help build out machine learning workflows using the training and deployment features of SageMaker, one of the topics that typically comes up is understanding the SageMaker inputs and outputs as they become key in building those workflows. SageMaker offers different options for training and deployment using fully managed environments, and we'll focus on 3 of those for now. First, SageMaker offers built-in algorithms that you can use to solve a variety of your machine learning problems. The grayed out boxes here indicate that AWS owns and maintains the container image for training as well as for inference. These images are stored in Amazon Elastic Container Registry, and you simply point to the repository for your model training and deployment. The inputs required for training a model are the algorithm-specific hyperparameters combined with your training data. Then the output, or artifact of a training job, is a model artifact that's stored in an S3 bucket that you specify. To deploy that model, you simply specify the S3 location of that model artifact, the AWS managed inference container image for that specific algorithm, and some configuration parameters for hosting such as size, number of instances, or whether you want to use SageMaker deployment features such as auto-scaling or A/B testing. Next, we have built-in framework. So with this option, AWS still owns and manages the container images for training and inference, but in this case, you bring your own training code and, depending on the use case, your own serving code potentially. This option is often referred to as script mode because you still are able to take advantage of pre-built container images, but using your favorite frameworks such as PyTorch, TensorFlow, or scikit-learn, among others. Finally, we have Bring Your Own Algorithm or Framework, which allows customers to bring any algorithm or framework for training and/or deployment on SageMaker. In this case, the inputs to training and deployment are all customer created and managed, including the code to build the SageMaker compatible container images, as well as those built images. The reason we're spending some time here is it's really important to understand the options for training and deployment, as well as the inputs and outputs produced for anyone that's responsible for building out SageMaker workflows. Let's now check out a quick demo. For this demo, we're going to build a SageMaker automated workflow to process data, train a model, and perform model evaluation using SageMaker's scikit built-in framework. The machine learning use case is to use an open dataset to predict whether a census responder has an income of greater than $50,000. The main focus of this demo is really in building an automated workflow, so let's assume some of our initial model building activities and experiments are complete. So we have a good understanding of our data. Maybe we've experimented with a few different approaches and we're ready to automate our training workflow, then promote our best performing model to a higher environment for deployment. Again, because the persona that performs this task can vary quite a bit and may even have varied skill sets, let's assume for this scenario, we're a data scientist or an ML engineer that is very comfortable working in Python. Now, SageMaker will provide the managed environments for data processing and training, but we also want to be able to automate the steps in our workflow. So for this, we're going to use AWS Step Functions, which is an AWS service that lets us create automated serverless workflows using native AWS service integrations that are built in. So we can take advantage of native integrations with SageMaker, but also with other AWS services that are common in machine learning workflows, such as Lambda or Glue. Step function workflows are typically built using a JSON-based language called Amazon States Language. However, many data scientists and ML engineers want to work within a language that they're already comfortable in, like Python. So for this demo, we'll create a step functions workflow using the Step Functions Data Science Python SDK, which is a layer of abstraction for creating and working with step function workflows using Python instead of learning Amazon States Language. So to get started, we'll first install or update the Step Functions Data Science SDK in the AWS and SageMaker Python SDKs. Next, we'll import the required step function and SageMaker modules that we'll use in our steps below. And then for this, we'll use two IAM roles within this notebook. The first is our SageMaker execution role, but we'll also need a step function service role that has permission to work with the AWS services that are part of our workflow. This visual represents the step function workflow we're going to create. So let's first configure what our workflow execution schema will look like. This schema represents the values that we'll pass in each time we trigger this workflow. So in this case, we're going to pass a unique ID that will be used for naming our SageMaker processing and training jobs. Let's now break down each step that we're going to configure, starting with our data pre-processing step. In this step, we'll use SageMaker processing, which gives us access to a temporary container environment that we can use for our data processing tasks. SageMaker processing offers built-in containers for Scikit, Spark, as well as the ability to bring your own custom container. For this, we'll be using the built-in Scikit container, where all we have to do is bring our own data processing script and our raw data, then SageMaker will automatically spin up an environment to perform our data processing. When our data processing task is complete, SageMaker will output our processed data to the S3 bucket we specify and automatically spin the environment down so we're not paying for unnecessary compute. Now for context, let's take a quick look at our raw data set. As you can see, we have a number of features on input, but let's say during our experimentation, we determined that not all of these features are really contributing to our prediction target. So in our data processing script, we're going to drop some columns like marital status and then transform some of the categorical features using one-hot encoding. So let's start with our workflow by first configuring a SageMaker processing job that can be used to execute our data processing script. To configure our scikit-learn processing job, We first create an sklearn processor using the SageMaker Python SDK, which allows us to configure what we want that processing job to look like in terms of compute, version of the scikit framework we want to use, and the execution role that the processing job should use. Then in the next step, we use a built-in helper function to upload our scikit pre-processing script from our notebook instance to an S3 bucket that we specify as input into our processing job. So now that we've configured the SageMaker processing job, let's now configure the corresponding step for our step functions workflow. We first need to specify the inputs and outputs for the pre-processing step. Now again, the input to our processing step is our raw census data stored in S3. Our pre-processing script in this case is coded to not only transform our data for use by our algorithm for training, but to also perform a split of our process data into training data, which we'll use as input into our training step, and test data, which we'll use in the final evaluation step against our trained model. Finally, now that we've configured the inputs and the outputs, we'll use that information to configure our workflow step using the built-in SageMaker integration with the data science SDK's processing step. We'll configure the step using the sklearn processor, the inputs and outputs we configured above, our script entry point, and we can also specify any script arguments. So in this case, we wrote our script to accept the test train split on input. So we'll pass in an argument that says we want to hold out 20% of our process data for our test data set. So now that we've created our data pre-processing step, let's create our model training step. In this step, we're going to configure our SageMaker training job, followed by configuring the step in our step functions workflow again. We talked about the different scenarios for training with SageMaker. So in this case, we're using a built-in framework scenario. And if you remember, this scenario, we simply need to provide our training script as input, combined with our training data to be able to configure our training job. In this case, for our training script, we're using a script we created that uses scikit's logistic regression. To configure the SageMaker training job, we'll import the sklearn estimator from the SageMaker SDK for our scikit training environment. We then configure our training job by specifying our training script and hyperparameters our algorithm expects for training. We'll also specify the output path, which is the S3 location where we want to store our model artifact. And we also need to select the compute environment. So in this case, we're selecting ML-M5 extra large. Now that we've configured our SageMaker training job, let's set up and configure the training step in our step functions workflow. So in this step again, because the data science SDK has built-in native integrations with SageMaker, we'll use the built-in training step and simply specify that we're going to use the sklearn estimator we created combined with our training data in S3 for this step in the workflow. So we've configured our SageMaker data pre-processing and training jobs in the steps above, as well as configured those steps in our step functions workflow. But now let's create our final step for model evaluation. So to evaluate how well our model is performing, we want to evaluate our model against data it hasn't seen yet. So to do this, we'll create another SageMaker processing job, but in this case, we're going to use the processing job for model evaluation by running a scikit script we created called evaluation, which is essentially going to load our model into our transient processing environment, then use our holdout test dataset as input to collect metrics such as F1, accuracy, and precision. In this case, our output as defined by our script will be a JSON file with these metrics captured and stored in S3. Given this is another processing job, the steps are going to look similar to our data pre-processing job, but our inputs, outputs, and the script that we're actually executing in our processing environment will be different. But again, we start with configuring our SageMaker processing job by specifying the sklearn processor with our compute environment and uploading our evaluation script to S3. We then go ahead and create our model evaluation step using the configuration of the processing job combined with the input and output definitions of our step functions processing step. Now that we've configured our SageMaker processing and training jobs and set up the configurations of our step function steps, we now want to create our workflow by chaining those steps together. So in this first step, we chain the steps we previously configured together. We then create the workflow, and then we execute the workflow, which you can see takes the input schema we defined at the beginning, where the input schema is the unique ID of each of our SageMaker jobs. Step functions will now execute each step in our workflow that we created above using the steps we chained together. The Data Science SDK also allows you to render the progress of your workflows directly within the notebook instance using render progress. So in this case, you can see that all our steps have successfully completed. Using the Data Science SDK, we were able to create a simple automated workflow using Python, which may be a more familiar option for many personas, but you can optionally create the same workflow directly in AWS Step Functions if you're comfortable with working with state language. We can see here that everything we created via the Data Science SDK is still completely visible within AWS Step Functions. Another really useful feature in the Data Science SDK is the ability to automatically generate and export the CloudFormation template for this workflow, so it can be used to duplicate your retraining workflows. So to wrap up, we just created a simple workflow to pre-process our data, train a model, and evaluate a model using the AWS Step Functions Data Science Python SDK, along with native integrations with SageMaker for training and processing. So we just looked at a simple training workflow, but what if we wanted to trigger a workflow automatically for retraining? Assuming we have a data pipeline that's providing the data that can be used for training, there's 3 common retraining strategies: scheduled, event-driven, or metric-based. With the first 2 strategies, we can set up either schedule or event-driven triggers via Amazon Event Bridge with our Step Functions workflow as our target. For metric-based retraining, we can monitor and create an alert that it's time to retrain based on something like data drift using Amazon SageMaker Model Monitor. All of these examples show Step Functions as the retraining workflow. So you may be thinking, do I need to use AWS Step Functions to build my automated SageMaker workflows? And the answer is no. While we focus this demo on using AWS Step Functions, there's a variety of options available when creating automated workflows for SageMaker. You can choose to use other workflow products while still taking advantage of the SageMaker features and capabilities at the same time. Many of the common workflow tooling like Kubeflow or Apache Airflow already have built-in support for Amazon SageMaker. The benefit of these integrations is you're able to take advantage of advanced SageMaker training capabilities such as managed spot training, distributed training, or hyperparameter optimization in transient compute environments that offer a wide range of compute options, and you only pay for what you use instead of training on the same compute that you're using to host your workflow tooling. You're also able to take advantage of managed deployment environments that can be easily configured for features like auto-scaling, A/B testing, or using Model Monitor to detect data drift. So we just went through using automation to create repeatable machine learning workflows. So let's now look at how we can layer in continuous integration and continuous delivery or deployment practices on top of that. So taking a simple Step Functions workflow to train or even deploy a model is great for repeatability, but what if we want to incorporate source and version control to improve our reliability and our ability to tie a specific trained model back to specific versions of code, configuration, or data? Also, automation allows us to easily repeat workflow tasks, but we also want to ensure that we're not only able to build faster, but with improved quality and reliability. This means introducing quality gates such as data validation, maybe explainability reports, or integration tests. We may also need to accommodate a multi-step release process, so where you have different stages, environments, or even different deployment strategies to consider. And then finally, by incorporating CI/CD practices, we can better provide end-to-end traceability, providing the ability to recreate and roll back to a specific version of a model when needed. Let's look at a few considerations to think about when architecting or designing your SageMaker CI/CD pipelines. First, identify your source code. A few slides back, we looked at the inputs required for SageMaker for training and deployment. However, in addition, you may also have infrastructure or configuration code to consider. And just as is true with DevOps, the same is true with MLOps, where we want to treat those items as code. So some examples here to include are CloudFormation templates that we might use for SageMaker deployments or CloudFormation templates for your Step Functions workflows. Next, identify your versioned inputs, such as common data science libraries and packages. Also, the actual container image are versioned inputs into your training and deployment jobs. Finally, with machine learning, we also have a new versioned input to consider, which is our data. Next, we want to identify and protect the version artifacts from our pipeline, which can include container images if you're using that bring your own algorithm scenario and building that container image within your pipeline. Another versioned output or artifact can be data. And the reason data can be a versioned input as well as an output artifact is our machine learning pipelines typically include a data processing task to take raw data and process it into the format that the algorithm expects for training. So in that case, for your data processing task, you can have a raw data set as input and your processed data set as your output or your versioned artifact. Next, we should identify the quality gates that we want and are sometimes required to incorporate in our pipeline. So some quality gates are common across pipelines, so things like training metrics or performing data validation, but others can really be driven based on company or industry-specific needs. Next, we want to identify our deployment strategy by first identifying whether our model will be consumed using SageMaker Batch Transform or if we're going to deploy to a SageMaker endpoint. We should also identify the SageMaker deployment features that we may want to take advantage of so we can ensure they're included in the scope of our pipeline. Also, we should be looking at a train once, deploy many strategy. So similar to DevOps strategy of build once, deploy many, the same should be true for your models. You want to train once and deploy to the target environments that make sense for your use case. We should also understand how our model is going to be consumed by integrating systems and applications. Finally, identify the operational needs up front. This is where cross-functional project teams are important to be able to understand the logs and the metrics that are important to each persona of your cross-functional team. Consider shared dashboards and visualizations that provide easy access to those metrics. So now that we talked about some of the considerations for building out a CI/CD pipeline, let's take a look at a common conceptual view. In the machine learning development lifecycle, a large portion of time is spent in model building, where data scientists and ML engineers are focused on understanding their data, feature engineering, and typically running numerous experiments where they're training and evaluating multiple potential models until they find that best performing model. At that point, we often see models committed to a model registry, which acts as a central store for versioned model packages, containing a lot of valuable model metadata, including how it was trained and what model versions are deployed across your environments. A model registry can also be a common trigger for executing a continuous delivery pipeline to deploy that best performing model to one or more target environments. You also see here a model retraining box in the lower left. So once a model is trained and deployed, we want to implement a retraining strategy. And that retraining needs to include the same data processing and training code that was executed in our model building environment. So as a result, we need to be able to reproduce that configuration to implement a retraining pipeline. So you may be thinking that this is great conceptually, but we have multiple accounts. We also wanted to integrate with other AWS services to build out our full pipeline. So how does this all fit in? So there's a variety of multi-account strategies that are well documented, and each AWS customer strategy is a little bit different. So we aren't attempting to prescribe a specific multi-account strategy here, but using this to really illustrate the ability to integrate with commonly used AWS services across environments, as well as in support of some of the unique aspects of the machine learning development lifecycle. SageMaker combined with the AWS Code Suite of products makes it easy to train in one environment and then package and deploy your models in another environment. So let's take a look at a CI/CD pipeline using some of the services you see here and building on the automated workflow that we saw in our previous demo.
In our last demo, we built out an automated workflow for training and evaluating our model. So let's assume we now have a candidate model that's performing well and we're ready to deploy it to a higher level environment using SageMaker managed endpoints. Because models can take hours or even days to train, we don't want to incur the overhead or cost of retraining our model again. So to create a bridge between our model building and model deployment environments, we're going to take advantage of a model registry. Again, depending on the skill sets of the team, everything we're demoing here could be done by a single role or tool, but frequently there is a need for a handoff or handshake between our model building environment and model deployment environments. First, let's do one final commit to our code repository for our notebook as well as our training and evaluation code. In this case, we're using code commit for our source code, and ideally you've already been doing this throughout your model building activities, but let's go ahead and do it one final time. Next, we're going to create a trigger indicating that we want to register and deploy the model using a simpler helper script that I created that takes a few input arguments. The first is project name, followed by the SageMaker training job name. The SageMaker training job name will be used to pull SageMaker information about the candidate model, such as the S3 location of the training script, the training data, and the model artifact. We'll use the information to register the model within our pipeline. Next, we provide the ARN of our step functions workflow, which our script will then use to extract the workflow to a CloudFormation template that could then be used for retraining. Finally, we provide a pointer to our code repository where we've checked in our model building code. We'll then go ahead and run our script to collect our data and put it to S3, which will then trigger the execution of our pipeline in Code Pipeline. Code Pipeline is the AWS service that we'll use for deployment orchestration. The helper script that we just created and used in our model building environment puts data related to our SageMaker candidate model in S3, and that S3 source is set up here as one of our deployment triggers. This pipeline can also be triggered by changes to infrastructure code and code commit, which holds CloudFormation templates and configurations that we'll use for our SageMaker endpoint deployments. In the next stage, we're going to go ahead and take the metadata about our model and register our model to the model registry. In this case, we're doing this step via a Lambda function we created that is inserting or updating rows into our model registry, which in this case is an Aurora serverless database, but DynamoDB is another common option here. You'll also notice in this stage, we're doing a code check as a custom quality gate that we created in Lambda. We previously committed our model building code into code commit. However, that's a manual task that can be prone to error. Because our SageMaker training job pulls our code from an S3 bucket that we can protect from modification, we can compare the code that a data scientist may have checked into code commit with the code actually used by SageMaker and flag any discrepancies as needed. So once we've registered our model and done a quick code check, we then progress to our next stage where we're going to deploy our trained model to a SageMaker endpoint in our test environment using CloudFormation. You may want to explore other deployment strategies such as AB, Shadow, Canary, or Blue-Green, but for simplicity in this case, we're going to go ahead in this deployment step. We'll create an endpoint if one doesn't exist, or update an existing endpoint with a new model version. We then update our model registry with deployment information to indicate the new model version that's deployed in our test environment. Next, we're going to go ahead and run a quick test against our deployed model to ensure our Lambda code that we plan to use for inference is in sync with the schema of our trained model. You can insert other tests or quality gates here, but for now, it looks like our steps that we have completed successfully. So we can now approve the model for deployment to production through a manual approval step that we've created. Once we approve, we'll go ahead and continue to deploy or update an existing SageMaker endpoint in our production environment, and we'll update our model registry deployment information to show the new model version deployed in our production environment. If we take a quick look at our model registry, we'll see data about our trained models as well as deployed models, which helps us manage our model lineage as well as have central visibility into our environments and what models are deployed where. In this demo, we showed you how you can utilize a model registry, the AWS Code Suite of services, combined with any custom logic that you want to implement via a Lambda function to start applying CI/CD practices for your machine learning pipelines.
In our previous demo, we saw how you can build out CI/CD pipelines for Amazon SageMaker using AWS native services. However, SageMaker can also be integrated with your existing CI/CD tooling, such as Jenkins or whatever tooling of choice that you have by using the CLI, the AWS Python SDK, or the Amazon SageMaker SDK. In this session, we covered how you can automate SageMaker workflows, allowing you to deploy quickly and in a repeatable manner. We then talked about including CI/CD practices such as source and version control, automated quality gates, to increase the reliability and traceability of your machine learning pipelines. We included a few resources here that we believe are helpful in applying MLOps practices to SageMaker workloads, as well as a link to a GitHub repository with multiple hands-on activities. We went through a lot in 30 minutes, but thank you so much for your time today, and I hope you're able to take away a few tips for implementing MLOps practices with Amazon SageMaker that can help you better manage, support, and scale your workloads. As always, please complete the session survey, and we truly value your feedback. Thank you.